Okay, so listen carefully here, guys. Give you the instructions for what we're going to do today. It's fairly straightforward. We're just going to be getting some of our own data to graph here, and to do that, we are going to use these incredibly awesome, and by awesome I mean crappy, cars that we have here from, I don't even remember where we got these, but they are awesome because they travel at a constant speed. Not in a constant direction all the time, but they travel at a constant speed. Okay, and that's what we need. Because what we're going to do is we're going to have them run down the hallway. All right, so we're going to go into the atrium, and they're just going to roll down the hallway, and we're going to mark their position on this measuring tape. Okay, every 5 seconds. Everybody follow me? All right, now, we're only going to need a couple of people to sort of gather our data. Everybody else is just going to write it down, all right, as we go. But it's fairly straightforward. We'll have the tape on the floor, okay, and we'll have one person for each cart. The person who puts the cart down on the floor, your job is to make sure it stays in a straight line. Okay, now to do that, you may need to gently encourage it as it rolls along the floor with small adjustment, not big adjustments. Okay, small adjustments with your toe just to keep it on track. Okay, because well, there's two reasons it doesn't go in a straight line. First off, they're old and crappy. But actually, the more important reason is the floor in the atrium isn't even close to being smooth. If you've ever looked like this at the floor in the atrium, which you will now because I've told you to, you'll see that it's got like bumps and waves and stuff in it because the guy who did the power troweling when it was all concrete must have been drunk. Okay, because it's just like there's humps in it. Yeah, it's awful. So they're always kind of going up side hills and stuff like that as they go, and so they kind of change direction a little bit. So you will have to keep it on course. What I mean by on course is try and keep it as close to the tape as you can without letting it drive onto the tape. Because unfortunately these little wheels have lots of tread and they tend to chew the tape. And then it's just a big mess. All right, so if you can just keep it as close to the tape as possible, okay, there'll be a person with a stopwatch and a person walking along with the little sticky notes. All right, and what they're going to do is every 5 seconds the person is going to say, now. Okay, or they'll count down 5, 4, 3, 2, 1. And the person with the sticky notes will put a sticky note on the tape exactly where the cart was at that time. Everyone follow? Yes? Okay, and then we'll know exactly where it was and we'll have the position data. Now, in order to make this a controlled experiment, and usually when I talk like that I'm giving away a hint, okay, a controlled experiment, we want to make sure that we measure from the same side of the sticky note every time. All right, because the person is going to set it down on the tape. Right, what we need to make sure of is that, you know, we're always measuring from, let's say, the leading edge. Because if we measure from the leading edge sometimes and the back edge sometimes, are we bringing in some error? Yes, we are. Okay, we don't want to do that. We want to be consistent. All right, so we're always going to measure from the leading edge of the sticky note. All right, everybody with me so far? Okay, so what everybody who's not actively doing something on each trial, your job will be, once the first sticky note is down, to start following along and writing down the data. All right, so recording the position. All right, at time 5 seconds, it was here. Okay, everybody with me? Okay, so nothing too terribly difficult. All right, so the problem we're investigating here is what's the relationship between distance and time of an object traveling at a constant speed. Now, we talked about 4 different kinds of relationships the other day, okay, and okay, they were, what was this kind? Linear. Okay, this kind was inverse, this was exponential, and this was inversely exponential. All right, now if this thing's traveling at a constant speed, what does that mean in terms of the distance it covers? Yeah, exactly. It'll have covered the same distance as it did the previous 5 seconds. Every 5 seconds it's going to cover the same distance. Everybody with me there? Yeah, okay. All right, so what kind of relationship do you suppose that's going to be? Yeah, it's linear, right? Because, I mean, this is saying, all right, here's time 5 seconds and it went 2 meters, and here's time 10 seconds. How far did it go? 4 meters, right? That's a linear relationship. Hopefully that's what we're going to see, right? That might be part of your hypothesis. Might be. Okay, so we have to generate a hypothesis about what kind of relationship is going on between distance and time for an object traveling at a constant speed. Gee, that should be pretty easy given that was just explained to us. Okay, remember, it's got to be if and then. Okay. All right. Now, for the design part, okay, variables. This one's kind of tricky. What are we manipulating here? Because we're not actually comparing the carts. We're going to run 4 different carts just so we get 4 sets of data, but we're not comparing them in any way. Right? What's our manipulated variable going to be? Actually, that's going to be our responding variable. See, it is tricky. Right, because we're going to determine how long the car runs for. Okay, we determine the length of the experiment. The length of the experiment determines how far the car is going to travel. All right, so it's a bit tricky because whenever people say or hear for the first time is the manipulated variable, they immediately think you're going to make time run faster, or slower, or backwards, or forwards, or you're not manipulating time. You're simply deciding how long the experiment is going to run for. Does that make sense? Okay, the longer I allow that thing to travel, the farther it's going to go. Okay, so what you're going to need to do here in the next few minutes is this. You're going to need to make a chart, except it's not going to have runner's name in it. Okay, it's going to have cart, because we are not going outside to do this. Okay, when it's nice, sometimes we go outside and we actually have people like walk and run and crab walk and stuff like that, so we get different speeds. Okay, but we're going to do this with the carts instead. All right, so your chart, I think, looks slightly different than this on your sheet. Yes? I think I fixed it. No, I didn't fix it. Okay, so what you're going to need instead, okay, is charts that look like this, except without any numbers in them already, because these are from last semester. All right, so you're going to need a distance versus time chart. So you'll have your cart, and you'll have 5 seconds, 10 seconds, 15 seconds, 20 seconds, 25, every 5 seconds, up to 40 seconds. We're only going to run these things for 40 seconds. Okay? If we actually have one with decent batteries, that gets it almost to the gym, okay, from the far side of the atrium. All right? So I need you guys to right now make a chart like that, okay, so that we can go out into the atrium and fill it in. All right, so here's our class data, guys. If you're missing any squares or anything like that, just fill them in. All right, and we're going to talk here shortly about what we're going to do in terms of the graph, in terms of the analysis, okay, and things like that. John, question? $9.92, is that right? Okay. Shoot. Okay, I'll need these other numbers here again. 9.92. What was the first one? Okay, and this was 8.14. 44. Okay. All right. So we've got actually really good data. They all had quite different speeds, with the exception of 10 and 11, which were close, but I think they'll be different enough that when we graph our data, they shouldn't overlap too much. Okay, we often have problems with that where you got 2 carts that go almost exactly the same speed and their graphs overlap. All right, now what we're going to be looking for here, okay, is that. Don't worry, I'll put it back up. Okay, we're going to have first a graph of position versus time, and we've already said that time is our manipulated variable. So which axis does it go on? X. Okay, manipulated variable always goes on the x-axis. In fact, I have never seen a graph where time was the responding variable. Okay, I have never seen a graph where time is on the y. Maybe because I've never done any really interesting science. I don't know. Okay, but in order for time to be the responding variable, you would have to somehow make time change, which, as far as I know, is beyond our control. It just kind of happens. Okay. No, because time doesn't actually change, only your perception of it. That's the weird thing with relativity. Okay? It doesn't seem like time is running any faster to you, but to other people whose perception of time is the same, it's actually slower. Yeah, it's all about perception. Yeah. the watched pot never boils idea? Yeah, if you're watching the clock, it seems to run slower. Again, it's all perception. I know what you're saying, Colton. Yeah. But it's because you're watching. If you were doing something else, remember how time flies when you're having fun? But a watch pot never boils. Is it fun to watch a pot heat up? Like, right? It seems like it takes forever. Time doesn't change. Our perception of it might change, but time itself always runs at the same rate. Okay. All right. So what we want here is a graph of position versus time. Position is going to be measured in what units? Meters. Okay. Time is going to be in seconds. All right. So we'll have that graph. You'll plot the points. I want all 5 carts on the same graph. Okay. I don't want 5 different graphs. I want one graph that has all 5 carts on it. Now, when you do that, how are you going to tell them apart? No, because graphs are always done in pencil unless you're doing this on Excel, in which case it will do it in different colors. Okay, but if you are doing this by hand, you will need to do it in pencil and use different shapes for the points. All right, so your first car you can use dots, and your second car you can use triangles, smiley faces, little hearts. I don't care. Okay, as long as you have a different shape for each one, and then you're going to need a legend. Exactly. You're going to need a legend somewhere on the graph, probably in the lower right corner of the graph, because there shouldn't be any lines or points there. Okay, put it there, and the little smiley faces are cart 3, and the little hearts are cart, whatever. All right, everyone with me on that one? So that's what we're looking for. Okay, if you do this on Excel, like I said, it'll do that for you. It won't make little hearts or little smiley faces, but it'll use different shapes and it'll use different colors as well. We want that graph to be big. Right? It should take up a full 8.5 by 11 sheet of paper. All right. So when you're making your lab report, you won't be able to, let's say, insert the graph into your lab report because we want it to be a full page. We want it to be big. So when you're looking at your putting your lab report together, okay, where we usually have procedure and your observations, you'll have this chart that you make, which you can insert, okay, and then you'll say graph, see last page, staple the graph on the back. All right. It's the same with your lab drawings, right? Like you couldn't put your lab drawings, you couldn't insert them. They were a full page. They had to be on the back. All right? So just make sure you tell me where the graph is in your lab report so I can find it quickly. Everybody follow? Okay. Now with Excel and Word, if you're using the two of those to put your lab report together, you can insert that graph into a Word file and just stretch it so it takes up the whole page. Right? You can do it that way. All right, so that's essentially that's kind of analysis, kind of observations. Your observations are the chart you have. The graph is the beginning of your analysis. Okay? The only analysis question there is asking you to calculate the velocity of each cart. Now, I often have people who cleverly figure out that they could do this. Right? We know how far the cart went, and we know how long it took. What was the point of doing a graph then, if I was just going to use that formula? The answer is there was no point to doing the graph. Thus, that's not the way you're going to calculate the velocity in this lab. All right? We are not using v equals d over t in that way. We are still sort of using it. Because once you have your graph done, okay, you should get, right, you'll have your points, and they're kind of going to go everywhere, well, but generally upwards. You'll draw your best fit line, but obviously your graph will have labeled axes and all that kind of stuff. Everybody with me so far? Okay. Now, what can I do with this best fit line? I can find its slope. What will its slope tell me if the units on this axis are meters and the units on the x-axis are seconds? Meters per second. Okay, so when I do this graph and I find, all right, here's one of the points I'm going to use for my slope calculation, and here's the other point. Okay, when I go y2 minus y1, okay, over x2 minus x1, right, I'm essentially taking distance over time. All right, but this is actually a more accurate reflection of what really went on. in the lab. Because you may have had a couple of points that were out a little bit more than others. Everyone follow? Like for example, maybe that last point you got, that where the wheel fell off. Okay, right? The last point. If not everyone saw that, but the wheel fell off of the one cart. Didn't affect it very much, but it might have affected it a little bit. Well, then this last point isn't as accurate as this trend is overall, is it? And if you use V equals D over T, and you use this value over the total time, are you as accurate as this line in telling me the speed of the cart? No, this line is more accurate than using one single point because it's the trend of all of them. Right? And that's why we want to use the graph to calculate the velocity of each cart. That's all there is for analysis, okay, is those calculations. Do you need to show me those calculations? Yes, and all your analysis is going to be is, here's the velocity for cart number 3. Show me the calculation. Okay, should you identify those points on the graph when you do it? Yes, please circle them, okay, on your graph so I know, because I'm going to look at that. I'm going to look at your slope calculation. I'm going to go back to your graph, and I'm going to make sure that you pick points that were on the line when you did your slope calculations. Okay, all of that is really important, so make sure you show me all of that work. Okay, if you show me all of that work, okay, you're going to get a good mark in the analysis portion of this lab. Right. You are going to have 5 best fit lines. Yes, 1 best fit line for each car, because they all traveled at different speeds. Agreed? Okay, so you'll have, so what I would suggest you do, if you're doing it by hand, okay, do cart number 3, do all its points, draw its best fit line, do the calculation before you do the next set of data. Because otherwise it starts to get confusing. Even if you're using different shapes and stuff like that, they're going to be kind of close together. We want to make sure that we get them right. Okay, questions on what you got to do? All right, and then same as always, you got your conclusion and evaluation after. Okay, so restate your hypothesis, explain why you accept or reject it. Okay, we're talking about what kind of relationship there is. If all of our carts give us, the ability to draw a best fit line, and that line fits with the points, then I think we're pretty safe to say it's okay. There were some obvious sources of error. Okay, especially the first couple of times when we were figuring out exactly how to do this. Okay, so you can say that when you're plopping this down, maybe that's not as accurate as it could be or whatever. Okay, just make sure that when you identify a source of error, you also suggest a way to improve it. And then you don't have to do the class discussion. Okay, we'll talk about those when I hand back the reports. Questions? All right, well, you've got another 25 minutes or so to work on that. Okay. Okay, guys, just I put the data from our class, okay, up here. If you lose yours or anything, the data for the lab is on my website. Okay, it's in it's in Science 10 Notes and Assignments. So you go to Science 10 Notes and Assignments, then click on Data and Observations for Labs. Okay, and it's in there. If you lose yours, now I made it so it's actually the handwritten version we did in class. Okay, with my red ink. And it is on there. Okay, so you would have to put it in your own chart. I do not want to see a chart inserted in your lab report that has handwriting in it. Okay, I want you to draw a table, okay, using whatever word program, okay, whatever word processing program you use, draw a table, okay, and fill it in. Remember that if you're drawing a table in Word, it's super easy. Okay, what do we need there? How many across was that? We got 9 across and 6 down, right? Okay, so you go insert table, right? And you can make 9 across, 6 down, boom, done. Right? Then you can type in each one what the title is and all that. Right under procedure. Okay, because procedure is where you get your observations, so that's where this should go. Okay, and I'm sure all the other word programs do that too. Right? Yeah, so that's what we want to make sure that we do there.